So let us solve a sample problem on energy in a simple harmonic motion. So the problem goes this way. A 0.15 kilogram toy is undergoing simple harmonic motion, it's SHM, simple harmonic motion, on the end of the horizontal spring with force constant, or the spring constant K, which is equal to 300 Newton per meter. When the object is 0.2 meter from its equilibrium position, it is observed to have a speed of 0.8 meters per second. So what are the following? This is what is asked in the problem. First is the total energy, total mechanical energy of the object at any point of its motion. Next is the amplitude of the motion. Next is the potential elastic energy at position x is equal to 0.06. And the kinetic energy at position x equals 0.06. And then the speed at this position x is equal to 0.03. So let us solve first for letter A, the total energy of the object at any point on its motion. Now we know that the total energy equals the elastic potential energy at certain position, plus its kinetic energy at that position. Kinetic energy. And what is this elastic? This one, elastic potential energy, that is equal to 1/2 kx squared plus 1/2 mv squared. That's 1/2 mv squared is the kinetic energy. So we know the spring constant k, and then when the speed is 0.8, then it means the object is at 0.2 position from equilibrium position. So you have x position and speed v. And we know the mass attached to the spring, ideal spring, which is 0.15 kilogram. And then the spring constant is also given, which is 300 Newton per meter. So we can solve for the total mechanical energy. So that is equal to 1/2 times 300 Newton per meter times the square of the position, which is 0.2 meter quantity squared, right, plus 1/2 the mass attached to the spring is 0.15 kilogram. So this is 0.15 kilogram, right? Times the square of the speed. We know the speed at 0.2 position, which is 0.8 meters per second. So this is 0.8 meters per second quantity squared. So we can solve using calculator. So that is equal to 6.048. What's the standard unit of energy? Joules. Symbol J. So this is the total mechanical energy. So we have letter A, the total mechanical energy of the object at any point of its motion. So next, let's proceed to letter B. Letter B, what is asked here is the amplitude of the motion. We know that the total mechanical energy is 1/2 k times the square of the amplitude. So the square of the amplitude is 2 times the total mechanical energy over the spring constant k, or the amplitude A equals the square root of 2 times the total mechanical energy over spring constant. So we can solve for the amplitude. So this is the square root of 2 times. We know that the total mechanical energy is 0.6.048. Right. The total mechanical energy is 6.08 joules. So that's 0.6.048 joules. Divided by the spring constant, 300 Newton per meter. We can solve for the amplitude using again the calculator. The amplitude equals 2 point, no, so the amplitude A equals 0.2007 meters. Right, so we have the amplitude, we also have the total mechanical energy. So let's proceed to the potential elastic energy when it is at position 0.06. So let us see potential elastic energy, US, that's 1 half kx squared. We know the spring constant, and what is asked is the potential elastic energy at this position, x equals 0.6. So we have 1 half k, spring constant is 300 Newton per meter times the square of its position, 0.06 meters quantity squared. Then we have the elastic potential energy at that position is 0.54 joules. So let's proceed to letter D. What is asked in letter D is the kinetic energy at position X. X equals 0.06. We know the kinetic elastic potential energy at that position, and we know that the total mechanical energy is the elastic potential energy at that position plus kinetic energy at that position. So meaning kinetic energy equals the total elastic energy, total mechanical energy, minus the potential elastic energy US. So what is the total mechanical energy? We have 6.048. All right. So this is 6.048 joules minus the potential elastic energy, which is equal to 0.54. 0.54 joules, right? So the kinetic energy at position X equals, so the kinetic energy at position X equals 0.06 is 5.508 joules. That's the kinetic energy at position X equals 0.06. Okay, next is letter E. What's letter E? What is asked in letter E? It is the speed. So we can use the equation of speed as a function of time, as a function of position x. So since x is given there, so we have speed, letter E, where the speed equals the square root of the spring constant k over the mass attached to the spring times the square of the amplitude minus the square of the position. So V here equals the square root of we know the spring constant, which is 300 Newton per meter, divided by the mass attached to the spring, which is 0.15 kilogram, okay, times the square of the amplitude. What's the amplitude? 0.2007. So the amplitude is 0.2007 squared, okay, minus, right, position 0.03 squared, right? Then the speed. So the speed at position 0.03 meters from equilibrium position is 8.87 meters per second. So that is the speed, that position. That's sample problem of energy in the simple harmonic motion. See you when I see you.